Let's explore Sharding strategies. Sharding involves partitioning data across multiple servers. This is done to improve scalability and enhance performance of databases and systems. Now let's see the benefits of sharding. Sharding enables horizontal scaling, allowing you to add more servers as your data grows. It also improves performance by distributing the query load across multiple servers. This ensures higher availability, as a failure will only affect a subset of your data. Also, sharding allows geographical distribution, which places data closer to your users to reduce latency. But sharding also introduces some challenges, like complexity since there are more moving parts to manage, and data distribution as it becomes important to ensure a balanced load. Joins across shards can become difficult as well, and data consistency should be maintained across all the shards. Here are some key sharding strategies for distributing data across shards. First, we have range-based sharding. This method divides data based on ranges of a key value, where each shard stores a specific range of the key space. Range-based sharding is simple to implement and efficient for range queries, but it may result in hotspots. Then we have hash-based sharding, which applies a hash function to the key to determine which shard should store the data. This distributes the data more evenly, which reduces hotspots, but it makes range queries inefficient. Finally, we have directory-based sharding. It uses a lookup service to track which shard contains which data, providing flexibility in data placement and easier resharding, but it introduces extra lookup overhead. Let's take a closer look at how hash-based sharding works. The function determine shard ID takes in a user ID and the number of shards, then calculates a hash value and uses the modulo operation to determine the shard ID. A hash function distributes keys uniformly across shards. This provides a consistent access pattern with a big O of 1 lookup time and eliminates the need to maintain range mappings. It also reduces data hotspots by distributing related data evenly. Now let's understand range-based sharding in detail. Data is partitioned based on ranges of a shard key, and range queries are efficient within a single shard. It works well for time series or sequential data, but it can lead to uneven data distribution. Range-based sharding requires rebalancing as data grows. Let's explore directory-based sharding in detail. In this approach, a client request goes to a lookup service, which maintains a lookup table. This table maps keys to shards. This provides flexibility in data placement and simplifies resharding operations. However, it adds extra lookup overhead for each request, and the lookup service itself can become a bottleneck. Consistent hashing minimizes data redistribution when nodes are added or removed. Only k divided by n keys need to be remapped on average, where k is the number of keys and n is the number of nodes. It supports dynamic scaling with minimal disruption and improves system availability during resharding. The function findNode calculates the hash of the key and finds the first node clockwise from the hash on the ring. Here are some sharding challenges and practical solutions. Joins across shards can be complex and expensive, rebalancing can cause downtime, uneven data distribution can lead to hotspots, and maintaining ACID properties across distributed shards is difficult. For solutions, we have denormalization, which duplicates data across shards to avoid expensive joins. We can also use consistent hashing to minimize data movement during rebalancing operations, and replication to create redundant copies of data across multiple nodes. Let's see some real-world examples of sharding. Google's Bigtable uses range-based sharding to partition data into tablets. Each tablet is assigned to a tablet server. It uses a 3-level hierarchy, and tablets split automatically when they grow too large. MongoDB supports multiple sharding strategies, including range-based, hash-based, and tag-aware sharding. It uses config servers to track shard metadata, where the shard key selection is critical for performance. Data is divided into chunks that can migrate between shards, and a balancer process automatically redistributes chunks to balance load. Instagram uses PostgreSQL with a custom sharding layer. They implement directory-based sharding with logical shards mapped to physical database servers. They use thousands of logical shards mapped to fewer physical servers and keep user data together on the same shard. They also have incremental migration capability. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.